We have talked about addition of velocities in classical physics as well. And let me give you an example of that, which I'm sure you'll recognize from first semester. So let's consider a man carrying a little girl in a sled. And let's say that the man and the sled, which is moving with the man, are traveling at 1 meters per second to the right. And then there's an observer on ground who's stationary. And the little girl then throws a snowball to the right in the same direction as the sled is moving at a speed of 1.5 meters per second. So the sled is moving to the right at 1 meter per second. The girl throws a snowball at 1.5 meters per second. So for someone on ground, for this kid on the ground, the snowball appears to be moving at 2.5 meters per second. So the way you would describe that is that the speed of the snowball with respect to the observer on ground is 2.5 meters per second. The speed of the snowball with respect to the little girl is 1.5 meters per second. Similarly, if the snowball was thrown in the backward direction, the velocity then becomes negative 1.5 meters per second. And the velocity of the sled is still 1 meters per second, positive 1 meters per second. And now what the kid observes as the velocity of the snowball is negative 0.5. So negative 1.5 plus 1 comes out to be negative 0.5 meters per second. So for the observer on ground, it's as if the snowball was moving to the left at a speed of 0.5 meters per second, because the sled itself is moving to the right at 1 meters per second. So that's an example of how additional velocity works in classical physics. So let's now take a look at how things change when you get to relativistic speeds. So if v was the velocity of the sled with respect to ground, and u is the velocity of the snowball with respect to ground, and u prime the velocity of sled with respect to sled, then the equation that describes the additional velocities is velocity u equals velocity v plus velocity u prime. And remember, these are vectors, so they can be positive or negative. Now, to see why this equation needs to change when you get to relativistic speeds, so consider that the snowball was replaced by a flashlight. So the girl is shining a flashlight first to the right. Then u prime will be equal to c, the speed of light. And the observer will measure the speed of light coming from the flashlight to be v plus c, meaning the speed of the sled plus the speed of light by itself. Which means what the kid will measure is the speed of light being greater than c. And that violates the second postulate of relativity, whereby both u and u prime should be equal to c, because the speed of light does not change depending on where you're measuring it from. So clearly this equation uh, is inadequate when it comes to when it comes to relativistic speeds, this equation for addition of velocities is inadequate, gives us wrong results. Now, without going into the derivation of this equation, I'm just going to give you the equation itself. So classical velocity addition works only at small speeds. At relativistic speeds, that needs to be replaced by this somewhat more complex equation. So u is equal to v plus u prime. That part is the same as it was in classical physics, but now there's this denominator of 1 plus v u prime over c squared. Now, this equation meets the criteria we had laid out before, that for small speeds, relativistic equations should look exactly like the classical equations. So if v and u prime were both much less than c, if v and u prime are both much less than c, then v u prime over c squared is virtually zero. And therefore, this equation becomes u equals v plus u prime, the same as the classical equation. So in the limit that u prime and v are much smaller than speed of light, this equation is exactly the same as the classical equation. Okay, so in order to use this, we'll have to, you can define u v prime, I'm sorry, u prime v and u in different ways. It helps to just be consistent, and one way that seems to work for me is that we define v as the relative velocity between the two frames. So in the previous case, we had the frame of the sled and then the frame of the kid on ground. And v is the relative velocity between those two frames. And then u and u prime can be used to represent velocity of the object in the two frames. So in the previous case, it would have been u is the velocity of the snowball as measured by the girl on the sled, and u prime would be the velocity of the snowball as measured by the kid on the ground. To keep the u's straight, u and u prime, we use u as velocity with respect to the Earth frame or some other privileged frame. And as we'll do a problem, this will become more clear what we mean by that. And then u prime would be the symbol to use for velocity as measured in the moving frame. So let's look at problem number 20. Okay, so problem 20 over here. Suppose a spaceship heading straight towards the Earth at 0.75 c can shoot a canister at 0.5 c relative to the ship. What is the velocity of the canister relative to the Earth if it is shot directly at the Earth? And in part B, if it is shot directly away from the Earth. So let's say that this here is the Earth, the round figure, and then that is the spaceship moving towards the Earth at 0.75 C. And then here is the canister, which is launched at 0.5 C directly towards Earth for part A. So going by what I just described, we will use V as the relative velocity between the two frames. In this case, the two frames are frame of Earth and frame of the spaceship. The spaceship is moving at 0.75 C towards the Earth. So presumably for an observer on Earth, the spaceship is coming towards them at 0.75 C. So V then is 0.75 C. And then the way we defined U and U prime, U would be used to represent velocity with respect to the Earth frame and U prime in the moving frame. So in this case, the moving frame would be the spaceship's frame. So as seen from the spaceship, the canister is moving at 0.5 C. Now, if you look at the wording of the problem, a spaceship can shoot a canister at 0.5 C. So presumably we're talking about as seen from the spaceship, the canister moving at 0.5 C. And it even qualifies that by saying relative to the ship. So all of that to say that the symbol to be used here is U prime for 0.5 C. And then we're looking for the velocity of the canister relative to Earth, so that's going to be U. So as you can see, the main hurdle would be to identify the symbols correctly. After that, it's just plugging it into the equation. So 0.75 C plus 0.5 C is 1.25 C divided by 1 plus. So again, since V and U prime are both expressed as multiples of C, the C squared ends up getting canceled out, and you're left with this. And the answer comes out to be 0.909 C. So that's the velocity of the canister relative to Earth. Now, for part B, if the canister is shot directly away from the Earth, the only thing that would be different is the sign of U prime. Instead of being positive 0.5, it will now be negative 0.5. And then accordingly, the equation is going to change, and you end up with an answer of 0.4 C. Let's consider problem 26. If two spaceships are heading directly towards each other at 0.8 C, at what speed must a canister be shot from the first ship to approach the other at 0.999 C, as seen by the second ship? So here there's no Earth, it's just two spaceships. So the velocity between them would be V. V equals 0.8 C. And these are the two spaceships here around the big circles. And then at what speed must, now since there is no Earth in this case, we have to decide which is the privileged frame of reference. So there's no hard and fast rule, but I'm going to call this second one as the privileged frame, which means it's U that is 0.999 C. because we want the canister to approach the other one, the second spaceship, at this speed. So presumably this is the speed as measured from that second ship. So U is 0.999 c, speed measured from the privileged frame. And what we have to figure out, at what speed must a canister be shot from the first ship. So in other words, we are looking for the velocity of the canister as measured from the first frame of reference, the non-privileged frame of reference. So U prime is what we are looking for. After that, you just plug in the numbers, and the answer comes to 0.991 c. One last topic in this section, which we will discuss in the next video, is Doppler shift.